Good afternoon, everybody. Okay, we were talking about dynamic Stokes equations the last time, so we got this far. Maybe I'll just start with a little bit of a interaction. I haven't done a poly in a while, so you can go to polyv.com if you want to direct MEEN40150 the course code, or you can scan this. And I think it should be active. Let me see. Okay. Okay, so I think it should be active. So just to begin with, okay, what the actual question? So last day we got to this Navier-Stokes equations, which is conservation of mass, conservation of linear momentum, or like forces essentially. And these are quite general equations. So my question is, in what way can these be simplified? And I suppose in practice we're going to go on to simplify them, but there are very many ways that they're simplified and used in practice. And by practice, I mean in commercial or open source CP codes. So you look at these equations, how can you get rid of terms? I suppose V is the velocity, rho is density. What else we got? P is pressure, gravity, viscosity. Yeah, so how can these be simplified? So I'll just give you a couple of minutes just to get you thinking. Hopefully somebody submits something. Or what can be ignored? Is there any way to make both equations simpler? Okay, somebody submitted one thing. Ignore gravitational effects. Very good. Yeah. Let's just drop this term. Any more? Incompressibility. So this is one that we're going to focus on. So this is a really common one. But some other people said when incompressible. So incompressibility, what does that mean? What does incompressible mean? How will these equations change? Viscosity if negligible. So what happens if the viscosity is negligible? So that's this mu here. So if the viscosity is 0, how will the equations change? Assume the problem's isothermal. So actually, more correctly, I should have put conservation of energy here as well, because we've density and that might appear in conservation of energy. So that's a more complete set. So assuming isothermal, which we're mostly going to do in this course, assuming the temperature doesn't change, no temperature effects yet, definitely so. Laminar flow. So laminar versus turbulent. How does that change these equations, if at all? Yeah, anyone else, if you have any last things, and I'll keep going, just in case anyone's finishing something off. Give you 10 seconds. Inviscid. So inviscid just means no viscosity. So yep, correct. So viscosity is negligible. Inviscid flow, they're the same thing. So assuming a negligible viscosity. Very good. Let me jump over here. Let me go through some common assumptions. So incompressible flow, and I'm going to show how the equations change, because that's going to kind of form the main CFD approach we're going to take in this course. Inviscid flow. So inviscid flow means viscosity is 0, and in that case, the equations are called the Euler equations. So Euler came along before Navier and Stokes and formulated a set of equations under the assumption that there's no viscosity. So in that case, There's no viscous effects. And if we think back to the effect of Reynolds number, so no viscous effects, that assumption is only appropriate under very high Reynolds numbers. So if you're doing flow over hypersonic flow over some vehicle, you might use an Euler solver. So an Euler solver is one where you ignore viscosity. Potential flow is a super simplifying flow. Creeping flow, that's let's say the opposite of Euler flow. So creeping flow is you assume that the flow is very, very slow, in which case you can ignore some of the transient or the convection terms. I don't mention it here as well, but steady state as well. So if it's steady state, all the DDT terms go to zero. And then there's some other approaches as well, simplifications or assumptions. So Boussinesque is if you're doing a thermal fluidic simulation, like for heating, ventilation, and it's how you can approximate the buoyancy terms. And then there's a variety of other approaches. One specifically we're going to look at is turbulence modeling. So we're going to have a lecture on turbulence modeling, how you deal with turbulence models. I've uploaded a section from this book, Fertiger and Perich. Section 1.7 from that book, they basically just have a paragraph on each of these along with some other assumptions, and they explain the difference between them. And for example, if you look at last year's past paper, if you can't find that, let me know. But you should be able to find it just on the standard info hub sysweb. But you'll see I ask at least one question, something like, what if the flow is inviscid, what does that mean? Or if the flow is creeping flow, what does that mean? Or something like that. Okay, so for average flux equation for an incompressible flow. So for the first lab you've done, we use an incompressible flow solver. So what does that mean? So if flow is incompressible, that means the density doesn't change. So this is once again a mathematical modeling assumption. Real fluids and gases are not incompressible. But we're going to assume the density doesn't change. So if the density doesn't change, and if you look at this equation, well, the density cannot change, then the rate of change at the time must be zero, so that must drop out. Where else does it drop out? Well, immediately we can see we have a divergence of density, which now is constant by velocity equals zero, so you can divide across the density. So this equation here will just become the divergence of velocity equals zero. So conservation of mass, this actually essentially is conservation of volume. So if the density can't change, conservation of mass and conservation of volume are the same thing. This is sometimes called the continuity equation as well. So if the divergence of velocity is equal to zero, then if we look over a momentum equation, we actually see the divergence of velocity term, the term appears here. So now we know that's zero, so that dropped out. And so we've got a couple of other terms over here. So we can get it to look like this, a little bit simpler. And how did we do that? We used a couple of assumptions. Just follow me as I walk you through. So this term here, we have a divergence of a viscosity by the gradient transposed. So with just some maths manipulations, we can rewrite that as the gradient of a divergence of velocity. And once again, this divergence of velocity is zero, so that means this term drops out. And then shorthand, a divergence of a gradient is just written as a gradient squared, or a Laplacian operator, it's called. So that's where this term comes from here. This one dropped out, this one dropped out, so now we're just left with pressure. And then typically in incompressible fluid solvers, they will divide across by the density. So they'll just divide the whole equation across by density. So the density only appears in the pressure term. And some fluid solvers actually will just bring this pressure over density. They'll define that as the pressure. So they call that kinematic pressure. So kinematic pressure is just pressure divided by density. So when we go to use open foam, it's incompressible fluid solvers. They're independent of, let's say, density, just to solve directly for pressure over density, called kinematic pressure. And then they will also often introduce a kinematic viscosity. So by kinematic, I just mean divided by density. So these will be the set of equations that we'll actually solve. So that completes an initial introduction, just an overview of the conservation equations that are used by these incompressible fluid solvers. So let me jump back to something we talked about maybe a couple of weeks ago, and that's numerical errors. So to remind you, the overall modeling approach is we start with a real life problem. Real life problem, we approximate it with some maths equations. That's called a mathematical model. We introduce some errors there. We approximate the geometry, the materials, the loading behavior, the governing equations. And that makes a mathematical model, which is an idealization of reality or an approximation of reality. Then we solve that in a computer, and that introduces numerical errors. So we said there's three main types of numerical errors: round-off errors, how computers store numbers; discretization error, which another name for that is mesh errors. So that goes to zero as our elements become very small. And then iteration error was the last one, which we didn't really talk about. So this is a bit more relevant for, or at least in your face, for when you're using a fluid solver rather than a solid mechanics solver. So we'll talk in these slides about iteration error, what it is, how can you quantify it, and how can you assure maybe it's small relative to other errors. So if you have done the first lab, which I guess is due this Wednesday, you will have been presented with graphs that look like this when you ran your fluid solver. And it'll say something, it'll say residuals. And when you press go, you'll see Fluent generates these and it updates them, and these lines are going down. And you'll see, okay, there's one called continuity, there's one called X velocity, one called Y velocity for the 2D case. It look like this. So you're like, okay, well, this must be something to do with the conservation of mass. This must be something to do with the momentum equation, which is a vector equation. We saw that in 2D, so there's two unknowns, lost them. And these seem to go down, and then it's doing these iterations, and this is a log plot. And these so-called scalar residuals, they seem to go down, and at some point it stops and says it's converged and it's done, and then there's your answer. So what are these residuals? When you go to do a transient problem, some of you may have started on the second week of fluent problems. If you do a transient problem like flow over the cylinder, then you'll see that you can have the zigzag shape. And then you may realize that, oh, this seems to be for each time step. When it goes to a new time step, these residuals jump up, and then they go down, and then when it's happy at some point, it jumps on the next step. So these residuals or scalar residuals, we'll see in these slides, are a measure of this iteration error. So this iteration error is a type of numerical error. And essentially, when we set up these solvers, we're saying that, okay, we want it to be 1 e to the minus 4. So when they get to 1 e to the minus 4, that's small enough, we think, for our problem. Then you can go to the next time step. Or you might see something like this. If you run some problems, maybe some other problems, I'm not sure for the labs, you'll see the residuals maybe start high, and then they kind of drop, and then you do loads of iterations, hundreds and hundreds, and they kind of are dropping, but very, very slowly. Or sometimes they get to some value and they just kind of oscillate and they don't drop. You can't drive them any smaller. And then what's going on there? So before I can explain what a residual is and how it relates to iteration error, let's just review the setup for a fluid problem. So imagine we flow in a pipe, and imagine pipe is, there's some pump upstream or high pressure upstream, and then we just have the outlet of the pipe is free to the air, so atmospheric pressure. So atmospheric pressure, that will be our gauge pressure of 0. And so then we have to define our governing equations, geometry, materials, and load. So governing equations, this is going to be like the first lab you did for fluid, so last week. We're going to assume that, well, it's water, it's not traveling that fast. We can assume it's incompressible, that won't affect its behavior too much. So we think, and it's isothermal, we'll assume that the temperature effects are negligible. So then we could use our Navier-Stokes equations as our starting point. Once again, that's introducing some errors, but it's an approximation. So our primary unknowns are going to be velocity and pressure. So velocity vector and pressure. And maybe we think it's axisymmetric, so in which case we're going to need 2 velocity components of pressure. So 3 unknowns. So our geometry, we're going to assume axisymmetric like we did in the lab. Is that correct or not? Well, it depends. So this seems like an initial simplifying assumption. So here's our axis. Axisymmetric is a special type of 2D. So if we know what's happening on this plane, if the problem's truly axisymmetric, then if we take a kind of pizza slice or a radial line in any direction, it'll be the same answer. So we only have to calculate on one of these planes. So we have an axis, an outlet where we have our 0 atmospheric pressure, and then we have an inlet upstream. There's some known, maybe mass flow rate or something like that, and then we have a no-slip wall, like a physical wall. Materials. So unlike in solid mechanics, the challenge is often describing a material behavior, like elastoplastic behavior or something. But for fluids, it's maybe a little bit simpler. Newtonian behavior is normally pretty good for many fluids. So in which case, if we assume a Newtonian fluid, we just have to define a viscosity. So we can look at the viscosity for water. If we're assuming the temperature effects are not important, then we can look it up for whatever the room temperature might be. And then loading. So for every boundary in our solution domain, we'll have to define a boundary condition and a boundary condition for each solution unknown. So when we were solving the solid mechanics problems, we had a boundary condition for displacement or force at every boundary. So they're the kind of complementary conditions. Whereas in fluid mechanics, we have to give a condition for velocity or pressure. Velocity or force or pressure. So the outlet over here, we'll specify a zero pressure. And at the inlet, we might specify a value for velocity, a non-zero value. At the wall, it's the same. You specify a value for velocity, so it's zero value for velocity. But you actually also need to prescribe conditions for the other variables. So at the outlet, we might know the pressure, but you have to say something about the velocity. So typically what they will do is you set the gradient, the normal gradient of velocity to zero. What does that mean? It means that if you were to take the value of velocity at any point on the boundary, if you plot it going inside the domain, so normal to the boundary inside the domain, we're assuming that that slope is zero. So we have to make some assumption about it because we can't solve the equations otherwise. So essentially we're assuming it's the streamlines are perpendicular coming down. That might affect the prediction. And then similarly at the inlet, we'll assume a zero gradient condition for pressure. We'll assume the pressure at this point is the same as the pressure at the point just inside the domain. And the same at the wall. So just to reflect back when we looked at the, there was a plate hole problem when we went through the same steps for a plate hole problem for solid mechanics. The same idea, when you look at a mathematical model, you're introducing different errors. So if we think, or to maybe pique your interest more in the final exam, I might say for a given problem, define what types of mathematical errors you might get. So if I say, here is flow of a car, if you're setting up the problem, what mathematical model errors you might you introduce? And the key thing is I want you to be able to distinguish between mathematical modeling errors and numerical errors. So that's the model, and you can see that that may have already introduced errors. So then the numerical process also introduces errors. So if you remember back, we deployed whole, so we took our idealized geometry, and then we made a discrete version of that. We represented it by squares, triangles, a so-called mesh, a grid. If we had a curve, we've no curve here, but if we did have a curve, then if we're using straight edged shapes, then that will be an approximation of the geometry. So you'll have a geometrical error as well, discretization error. So the discretization error actually has a geometric component as well as the, let's say, the classic mesh error interpolation. So a little bit different language, nomenclature, parlance. So we're talking about a finite volume method. We could do the finite element method here, but many of the commercial CT codes use finite volume method. So we're going to talk a little bit about how that's different. So often these elements are called cells or control volumes in finite volume method, but they're the same as elements. It's just they use slightly different words in the literature or books. So they will call them control volumes or cells, but they're the same as an element. In the finite element method, we define the unknowns at the vertices. Then we assume the interpolation function within each one of them, and then we derive out our stiffness matrix. Whereas in the finite volume method, one of the most common forms, the cell-centered finite volume method, they store the unknowns at the centers of the cells, or the centroids of the cells. And then they do this discretization process. They take these equations, apply to each one of these cells or control volumes, and they rewrite these equations in terms of the velocities at these cell centers and pressures at these cell centers. So how does that work? Well, we're going to have a couple of slides next week or lectures on the finite volume method, the same way we did for finite element. So I'll go through how that process works. But essentially, it will just convert these continuous partial differential equations into algebraic equations. And by algebraic equations, I just mean like a set of simultaneous equations. Equations where it's some number multiplied by the value of velocity at this location, plus some number by the value of velocity at this location, plus et cetera, et cetera, et cetera. And the same with pressure. And we'll have a momentum equation, which has a vector velocity, and the pressure equation, which is a scalar. So in 3D, we have 4 unknowns at each cell center. So if we can form those 4 scalar simultaneous equations for each cell with 4 simultaneous equations for each cell, we can do the same thing for cell 1, cell 2, cell 3, the whole way up to cell n, so like 100 cells or 1,000 cells or 1,000,000 cells or whatever. So then if we have 4 scalar equations, then we'll end up with 4m overall equations and 4m unknowns. So pressure and velocity in each cell. So we have a big bunch of simultaneous equations, and then they can be solved. So the same as the finite element method, except the unknowns are stored at cell centers rather than at vertices. When I got to talk further about the finite volume method, there are a continuum of flavors of numerical method. So there are actually vertex-centered finite volume methods as well. But I'm going to talk about the most popular ones, which are cell-centered methods. So just drawing your attention to this equation at the bottom, essentially at the end of all this, our simultaneous equations for all our unknowns are in the same form as finite element. We have a big matrix, like a stiffness matrix, and then we have a list of unknowns, which this case represents the velocity and pressure at the cell centers. And then we'll have something on the right-hand side, which we previously called like a load or force vector. And so it'll end up being a very similar system of equations. So this matrix will be like a stiffness matrix. It'll be sparse. Typically it's symmetric. It doesn't always have to be symmetric, but it'll have very similar characteristics to the finite element approach. Like in the finite element method, conceptually, then we would solve this system by, we can calculate the inverse of this K matrix. We can multiply by the inverse on the left and on the right. So K inverse by K is pi, that cancels out. And then that means our solution, the cell center velocities and pressures, are equal to the inverse of K by F. So I'm normally saying conceptually that it's done like this. Often calculating the full inverse, which is a dense matrix, doesn't happen because that's very expensive. So there's often approaches that you can get the same answer without directly calculating this K inverse. You calculate this product directly instead or something like that. So the full inverse isn't normally calculated and stored. Once you have velocity and pressure, then you can calculate things like the shear stress or something like that, which are a gradient of velocity, for example, or mass flow rates, or forces on a boundary, or vorticity. They're all a function of our primary unknowns, velocity and pressure. Okay, so I thought these slides were meant to be iteration error, so I'm getting to iteration error. So the reason that it's a bit more in your face iteration error when we're looking at fluid mechanics problems is the presence of this so-called convection term or advection term. So there's no way we can write this velocity by velocity as a number by a velocity. It's a squared term, it's a so-called nonlinear term. So we can't discretize it to have K not a function of velocity multiplied by just some unknown velocity. So to write it in this form, we will have to have K a function of velocity in some way. So for example, if I have viscosity by velocity, then I can just put the viscosity here and the velocity there, and that's a linear term. But if I have velocity by itself, that's a nonlinear term, and that cannot be split into a coefficient, which is not a function of velocity, by the velocity itself. So how do we solve this? It means that typically K will be a function of velocity, and that means we have to iteratively solve the system. We have to solve the system over and over again. So maybe we'll solve it, calculate K using the latest velocity, solve the system to get a new velocity and pressure. Then we will recalculate K using the latest velocity and pressure, and then solve that again and again and again and again, and keep doing that until the system converges. So this nonlinearity happens in solid mechanics as well. So we looked at elastic systems, but if you have an elastoplastic solid, one that undergoes permanent deformation, then in that case, K will be a function of the displacement, and you have to do the same thing. Or if you have large deformations, then K K would be a function of the displacement for solid mechanics and finite element as well, or if you have some nonlinear boundary condition like contact or fracture or something like that. So this is not limited, iteration error is not limited to fluids, but it's just maybe a poor interface. So how does this iterative solution procedure work? Well, there's various approaches. Newton-Raphson method you will have heard of is often used in finite element, and it can be used in fluid mechanics, but the same general procedure is used. You define a loop. This is called a do-while loop. Do-while loop is just do this thing and then check if you should do it again. So do it at least once and then check if you need to do it more times. So we'll have K, which we're now saying K is a function of the velocity. So we'll calculate it using the latest velocity. So we know all the cell center velocities. Calculate this K matrix, which will be a function of viscosity and the spacing of the mesh. And then solve for the velocity and pressure at the cell centers. So we have our linear system here, and we're going to solve this system and then update this I index and then keep going while K, U, and P are still changing. When they don't change anymore, then we've converged. But then the question becomes is, how do we know when it's converged? How do we know when this system is no longer changing? So we know the answer is converged when, if we take our latest velocity, if we calculate K, multiply it by our latest pressure and velocity here, if it's exactly equal to F, then we know we found the right answer. To put that a different way, if I just bring all this onto the right-hand side, or move it all to the left-hand side, multiply by -1. So I'm just moving here to the left-hand side. So the difference between F and this by this, using our latest pressure velocity, is equal to 0. Then we know we've found the exact answer to this set of simultaneous equations. But in general, during the iteration process, they will not be exactly equal to 0. These things will not cancel out exactly. And we'll have some error. This error here we're calling, or this error is called a residual. So why is this residual not 0? So think about it. We start off with velocity field of 0 everywhere. So let's calculate K using assuming that velocity is 0. So you get some terms for K. It'll be a function of viscosity as well and spacing. Solve for U and P, holding that U constant. That will give you a new U. If you sub that back in, now that velocity is non-zero everywhere, these K terms will change. So that means that if you sub that back in, that will no longer balance exactly. There'll be some error. So maybe if you sub it back in and solve over and over again, it will approach convergence. But at any iteration, there will be some difference between the left and right-hand side. And that difference we're going to call a residual. So if this equation represents a conservation of linear momentum, like a force balance, then this residual can be thought of like a force imbalance for every cell. So that's a way to think, another way to think of it. Or if it's representing conservation of mass, it might be a mass imbalance per cell. So this residual, which is a number for every cell in this case. So if we 3 velocity equations, 1 pressure equation, V will be 4 scalar numbers for every cell, an imbalance for each conservation equation per cell. So that's a measure of iteration error. So if I do flow in a very large pipe versus flow in a microfluidic device, then this residual will be very small in a small device rather than very big in a big device, because it has units of force, for example, like they're absolute units. So if we were to write a solver and say, oh, well, when this gets below 1 Newton, that's small enough, that only would make sense if 1 Newton is small relative to your problem. But for a microfluidic device, that might be huge. So typically we will scale these residuals. So rather than just saying when R is below some tolerance, we will multiply R by a scaling factor S. And that scaling factor should make the definition of your residual dimensionless and independent of the scale. So for example, you might divide it in some way by the dimensions of your geometry or something like that. There's various ways that can be calculated. So then if we come back to our conceptual iterative solution process at each time step, we will solve our system K, like Kx equals F, where X is our velocities and pressures. We'll then define our scale residual, and that's 4 numbers for every cell, and maybe we just sum them all up, or we take the averages of them, or we take the maximum, and that gives us 1 individual scalar. So that's the imbalance, the difference between the right and left-hand side, scaled in some way. And then we keep going until the scaled dimensionless residual has got below some tolerance. So if we go back to our slides, oh, it might be too far to go back. Let me see if I can go back to the very start. Say here. So in this case, the residual is actually defined separately for each of the equations. So this is the average, typically, of the continuity residual for all the cells. This is the average of the x velocity or the momentum in the x direction, the force imbalance for every cell, and this is the y imbalance. So you can see that the y imbalance has gone down very tight. It's very low. It's got to 1 e to minus 6. In this case, I can't remember. Is that e to minus 3? I think each of these has its own tolerance, but it's whichever one takes the longest to converge. So I think we have to wait until the continuity error gets below 1 e to minus 3, and then after that 33 iterations, it's considered to be converged. So these residuals are the so-called scale residuals. They're dimensionless. So if you run the problem small or big, if it's the same physics, just scale down, it should show the same behavior. But this shows that these errors are not driven to 0. They're just driven to what should be considered small for this problem. And unfortunately, small for one problem may not be small for other problems. All right, so give me a second to skip back forward. Lots of things moving around. I like things moving around in slides. All right, almost. Just a pain with Zoom. For some reason, doesn't let me exit the presentation, so bear with me while I get through all the slides again. Okay, so our scale residual. Oh, I actually had the slide after all that. Oh, very good. I know for next year. Okay, so we solved the system, and then these are scale residuals. So we can plot these to monitor them as well. So you don't have to plot them to monitor them. When Abacus is solving a nonlinear problem, it's not plotting them. It just gives you the output of how many iterations it took, or if it fails, it'll just tell you it failed, make some other time step or do something like that. But this historically is just what they do in fluid mechanics. They will plot them. But also a benefit of plotting them is these are going down, but what happens if they don't go down? Then it knows that this iterative process is not working, and then you need to maybe reconsider your boundary conditions or your mesh or geometry or something like that. So when you choose these, they'll have certain defaults in Fluent. So they might say 1 e to minus 3 is fine for the continuity error. Maybe 1 e to minus 4 or 5 is fine for the momentum errors. But they're just broad rules of thumb, and they may not be appropriate. So, for example, there's no point in having a very fine mesh having a very fine discretization error if your iteration error is dominating the solution, for example. So whatever you're interested in, you might do a sensitivity analysis to see if this iteration error affects it. If you're interested in the force on a boundary, force on a wall, you might run that with 2 different iteration error tolerances. And if it doesn't change at all, then it's fine to use the loose one. Maybe even make it looser. But if it's very sensitive, then you might need to go tighter, because that might be the dominant error. So it's more important probably in fluid mechanics than solid mechanics. Any comments or questions or anything else? Or even anything related to labs? No? Okay. So I'll start on maybe for next 10 minutes or so. I'm going to look a little bit closer at the Navier-Stokes equations in their incompressible form. Then in future slides, I'll go through a bit through the finite volume method, and then I'll talk about some practical considerations like choice of boundary conditions and fluid test cases. So these are Navier-Stokes equations for an incompressible and isothermal fluid. So we have a conservation of mass, which is the same as conservation of velocity, or conservation of volume. We have a inertia term, a so-called convection term, These are viscous stresses, these are pressure stresses, and then gravity. So these are surface forces, these are body forces. This is essentially Newton's second law, mass by acceleration equals sum of surface forces, body forces, and the surface forces have a viscosity component and a pressure component. So take this divergence of velocity. So we kind of looked at this already from a conservation of mass perspective, but let's just see what it means for a conservation of volume in this case. So imagine some fluid flow flowing, and these are the streamlines, the path lines. And imagine we have a small area that's delta x wide, delta y tall, and maybe it's 2D, but you could assume it's 3D with a depth of 1. And consider the stationary square region of that flow. So let's calculate the net flow into and out of this region, kind of like we did before for conservation mass. So at each face, we will have some distribution of velocity, but let's say just take the average in the center or the point at the velocity at the center of each face. So you have a velocity vector v1 on the left, v3 on the right, v2 on the top, and v4 on the bottom. So you can see that v2 and v3 are leaving, they're bringing mass and volume out, and v1 and v4 are bringing mass into this region. But like before, you can decompose these velocity vectors into the normal component, the one perpendicular to the boundary, and a tangential component. So any tangential flow, if you just have tangential flow fully tangential to the boundary, that will create no mass flow in or out. So it's only the component that's normal to the boundary is actually bringing mass in or out. So we'll just look at the normal components. So for V1, if this is the x direction, we'll say V1x, V3x, they're the ones we care about. V3x is bringing mass out, V1x is bringing mass or volume in. V2y is bringing volume out, V4y is bringing volume in. So the volume flow rate through any one of these faces is just the normal velocity by the area of that face, like we did before. So if we take this normal component velocity multiplied by the area, that gives us some meters cubed per second flowing through that face. So if I'm at any face, if I take to get the normal component of velocity, it's the normal vector rho by the velocity vector, so rho by column. So we can write this as the magnitude of the area. This gamma is the area vector, so the magnitude of that area multiplied by the normal by the velocity. So if I want to calculate the net volume flow into this square, I can sum over the 4 faces. So this summation in the bottom corner here, I'm summing over the 4 faces of this q dot, my volume flow rate. And so that's the normal velocity by the area of that face. So I can write that as the normal velocity of face 1 by the area of face 1 plus 2 by 2 plus 3 by 3 plus 4 by 4. So 4 components. So if I actually just plug those in, I can see, well, if I take V1, the velocity here, V1x, multiplied by this area. So that area is delta y, right? So it's delta y by 1. So that's why I have a delta y there. Then for the V2, so it's V2 here, and that's multiplied by delta x, because the area is delta x. Similarly for V3, it's V3 by delta y, because that's the area. And V4 is multiplied by delta x. So these delta x and delta y's are just the area, not and the signs are indicating whether flow is in or out. So if I just clump together the flow in the x direction versus the y direction, so whatever is multiplying delta y, so I have a v1x by delta y and a v3x by delta y, I'll see that it's v3x minus v1x by delta y. So the difference in this vector and this vector represents the net inflow in the x direction. And the difference between this vector and this vector here is the net flow in the y direction. So you can see the total net flow is the sum of all of those, which is fine. So I arbitrarily chose a control volume, a region that's delta x by delta y. So just to make it independent of those, I'm going to divide by delta x and delta y. So I'm going to divide by the volume. So to calculate the volume flow rate per unit volume, because partial differential equations are given in per unit volume. So I'll divide this Q meters cubed per second divided by meters cubed. So divide by delta x, delta y. So dividing this by delta x, delta y, the delta y cancels out, you're left with delta x underneath. Divide this by delta x, delta y, you're left with delta x cancels out, you're left with delta y underneath. So that's on the right hand side here. So you have b3x minus b1x divided by delta x, b2y minus b4y over delta y. So the difference in velocity here divided by that distance, the difference in velocity here divided by that distance. So now let me let this delta x and delta y go to zero. Imagine that these this region I'm letting become smaller and smaller and smaller and smaller. So in that limit, these delta x and delta y's, you can see it's b3x by minus b1x. So velocity here minus velocity here divided by the distance. So that is just the definition of a derivative, a partial derivative. So as this delta x goes to zero, that is just calculating the gradient or the rate of change of vx in the x direction. Similarly, this one is just the rate of change of the velocity in the y direction in the y direction. So the flow rate per unit volume, as I let this volume go to zero, is just dvx dx plus dvy dy. If I split that out into the so-called differential operator vector, so ddx and ddy, row by column, you can see that gives you the same thing. So this thing here is just the same as writing the differential operator, this nabla, row by column. So ddx by dx, ddy by dy added together. So similar to what we did with conservation of mass, just by looking at the volume flow rate through this small region and letting this small region go to zero, you can come to the realization that that just means if the volume is conserved in this, then it just means the divergence of velocity must be zero at a point. So we can see the divergence of velocity means conservation of flow rate for a region. So when you see this divergence of velocity, that just means at any point where this is applied, you're saying that whatever flows in must flow out. So there can be no accumulation of volume at a point. And that makes sense for an incompressible fluid because you can't have more fluid flowing in than flowing out because then the density would have to change and that would violate the incompressibility assumption. So I will leave till Wednesday to do a similar analysis on conservation of linear momentum. Thank you.